So as we know that water is very valuable, yet we don't know the full value of actually water. So in this talk, I will share with you that how we used a fully coupled actually model to actually value like find like a full value of water and its ecosystem services. Water supplies a slew of ecosystem services, and few examples are water filtration, water supply, nutrient cycling, carbon sequestration, and many more. These ecosystem services, like some of them are actually material and some of them are the non-material services. However, all of them are very valuable. A way to actually assign water a value is through mapping and valuing these ecosystem services. If we want to map and value these ecosystem services, we need to we should be able to actually map water fluxes which are taking places in the water cycle. And for these kind of fluxes, we need like modeling tools which can map them. And if you look at actually literature, there are so many modeling tools which can be used or which are being used for mapping of these fluxes. To see that what are the most commonly used tools, we have reviewed the literature. So you may be thinking that these are the tools like MikeSheaf, eFlow, and so on. But when we reviewed the literature from 2010 to now, we found out that there are three major modeling tools which are being used for mapping of ecosystem services, the water ecosystem services. And the first one is actually Invest tool, then the SWOT, and then we have actually artificial intelligence tool areas. And the most commonly used models are SWOT and ecosystem services specific tool Invest. SWOT is basically a water model which can map a number of fluxes, and at the same time it can compute the water quality and water quantity at a watershed scale. However, if you look at Invest model, that is a simple tool, and that can map actually water over annual cycle using simple water balanced technique. Ecosystem services community thinks that the SWOT model is a sophisticated tool, therefore they are more kind of inclined towards SWOT. However, both of these modeling tools have their weaknesses and the strengths. So we actually put forth a selection criteria for these two types of actually models. And the first thing model users need to think is that why they want to use a model. If they just want to map water ecosystem services, they can go with the SWOT. But if they want to map a number of ecosystem services and they want to map their socioeconomic value, then they go for ecosystem services specific tool, which is this Invest tool. Then there are many data sets and skill sets and geological conditions, spatial and temporal scales, which we need to take into consideration, and when we are just like considering SWOT or Invest tool. But what is the next? Because both of these models cannot map certain phenomena. For example, they cannot map the subsurface and the surface water exchange. And that is a key phenomenon which supports many ecosystem services. For example, water supply, water quality, nutrient cycling, and many more. Those are directly linked with this subsurface and surface water exchange. And at the same time, if you look at this ET, that is the major thing which is being supplied by this surface and subsurface water exchange, and it supplies a number of ecosystem services because the land users use the water through ET, and then they supply ecosystem services, and therefore it is a very valuable part. But most of the time in the water cycle, we think that this is the water loss, but actually it is something which is being used by the ecosystems. So if we want to map the water contribution towards ecosystem services supply, we should map this phenomenon called ET, evapotranspiration. So for this one, this actually takes the water from three water storages. Those are the surface storage, soil storage, and the subsurface storage. So if we want to map ET, we should be able to map all these fluxes which are taking place in the water cycle. And the simple tools cannot map these fluxes. Therefore, we need more actually modern tools, which are the fully coupled tools, like for example, PowerFlow, MikeShe, and AGS model. AGS model is one of the top tools which can be used for mapping of water ecosystem services. And why do I say this? Because it can actually map all the fluxes which are taking place, or actually most of the fluxes which are taking place in the water cycle. As you can see that the subsurface flow into the surface, or the surface flow, and it can link ET with these water storages. Therefore, we have used this model to map water fluxes and water ecosystem services in the Sauk Nation watershed. This watershed contains many land use types, and the precipitation is 940 millimeter. And we have applied this model from 2000 to 2017, 18 years for 18 years. And this model needs a number of data sets. For example, it needs land use data, climate data, geological data, and much more. So here I show the 3D perspective of the Sauk Nation watershed, and you can see that this model uses the 7 subsurface layers. So using all this data, and we have actually fed all this data into the model, and we simulated many variables, like, for example, flow rate, ET rate, the subsurface storage, and the surface storage change in the watershed. So this is the time series data. So now we have to link, or we have to accumulate this at an annual cycle, and you can see that there is now have accumulated the data, and here is the change in the volume of these variables. And if you look at from 2000 to 2017, the 2012 just stands out, because ET is the largest and the precipitation is the lowest. So actually in this year, the main support to actually ET was coming from the subsurface and the surface storage, which are just like declining in this year. So this is with respect to the change in actually volume. But what if we want to see the change in the subsurface and surface storage with respect to their size? Because the surface storage is small and the subsurface storage is much bigger in volume as compared to the surface storage. So we have to compute the standard scores. Therefore, we have computed the standard scores, and here you can see that the change in these variables with respect to their size. And again, here you can see that the surface change is more than the subsurface change with respect to its size. Although its size is small, so the contribution by volume is small, but with respect to its size, it is more than the subsurface storage. Now, we have to economically link these changes in the storages or use of the water towards ET and finally towards ecosystem services with economic values. And for that, we have to economically evaluate the Sauk Nation watershed. We have selected 13 ecosystem services from the watershed, and we have applied a famous approach called BTM approach, which uses the land use types and the unit values. And we have economically evaluated the Sauk Nation watershed, and we came up with a value of $2.33 billion per year. Now the challenge was to actually variate this value over a time period of 18 years, from 2000 to 2017. So we have collected data, NPP data, and we have actually applied on this mean value, and we have just like variated the value over the modeling period. And the variation is from $2.22 billion to $2.49 billion from 2000 to 2017. So now we have the economic values of ecosystem services and the total water which was used towards ecosystem services supply. And now we can calculate or compute every product of water. This is basically the total value of ecosystem services divided by the total water used towards the supply of those services. So basically, this is the value of ecosystem services per unit use of water. So just like putting information in this formula, we came up with these values of ecosystem services water productivity from 2000 to 2017. And as you can see that in the 2012, the value is low. And as I've shown that more water was used and the less ecosystem services were supplied, therefore the value is low. But if we look over this modeling period, the value changes or varies from 0.91 to $1.08 per cubic meter. Now we need to evaluate the subsurface and the surface storage consumption towards ET or the green water. So for that one, we need to develop just like a production function between the value of ecosystem services and ET consumed towards the supply of ecosystem services. And if you look at the slope of this line or the production function, that is 0.45, and that is actually the marginal value of water in the South Nation watershed. So the value is 45 cents per cubic meter. So now we can apply this value, and we know from our actually modeling or simulation volume of the water, the total as well as the subsurface and the surface storages consumed towards the supply of ecosystem services, and we can just multiply these two numbers, and we will have the value of the storages or the total water consumed towards ecosystem services supply in the South Nation watershed. So applying this formula and feeding all information into this formula, we found out these values. And as you can see that the value changes from 950 million to almost 1150 million for the South Nation watershed. And if you look at the value in 2012, that is the maximum value because actually more water was used in this time because the precipitation was low. Now, if we want to split this value into the subsurface and the surface storage contributions towards ecosystem services supply, we need to feed their value or consumptions towards ecosystem services, and we came up with these values from 2000 to 2017. And you can see that the surface water storage contribution is basically minuscule, and that is below $30 million. But if you look at the subsurface storage contribution, that is much bigger. So it clearly shows that when it comes to the ecosystem services supply, the subsurface storage plays a major role. And its value varies from 650. Actually, mean value is almost like $650 million per year for the South Nation watershed. So the key takeaways from the talk are that the maximum value for the green water was in the year 2012, and that was almost $1 billion per year. The most important thing is that for that $1 million, out of that $1 million, or for that $1 million, 72% of the water or actually value was coming from the subsurface water contribution. So if we look at from 2000 to 2017, over this modeling period, it shows that the subsurface contribution was 52 to 73%. And the surface water contribution was really small, 2 to 3.6%. So the results of the study clearly show that the subsurface water plays a major role in the supply of ecosystem services from a watershed. Therefore, the results of the study can be used for effective management of the subsurface water storages in the watersheds. We have submitted a paper out of this study, which is in the review process. And for this work, I would like to thank Steve Fry and our Eco2 team. They were very supportive, and I would like to thank you for your time and attention.